to trickle in. All right, well, 5 seconds to the hour, according to my clock at least. So I just want to say hello to everyone and welcome to the first Rocky Worlds discussion of 2026. My name is Limble Christmas, and I will be moderating today's discussion, which will be led by Moa Persson from the Swedish Institute of Space Physics, who will be giving a talk on Venus defying the solar wind without a magnetic shield. And just before we do that, just a couple of netiquette notes. We ask that you ideally use your full name on Zoom so we know who you are and we can wave at you. If you have any questions during the talk, it would be great if you could save them until afterwards because we will have a Q&A session. And at that point, you can raise your hand with the raise hand button and we can call on you. And when we call on you, it would be great if you could maybe turn on your video before you ask your question. And if you're not able to do that and you want to just write your question in the chat, that's totally fine too. And if you do that, I will just read them out to you afterwards. And that also goes for the questions that are on YouTube. Hi, YouTube. And I think that's everything. Yeah, keeping our videos off during the talk and videos on when you're speaking. Yes, that's everything. Okay, great. So in that case, I will hand over to Moa. Thank you so much. Please take it away. And I'll stop my screen share now as well.
Thank you very much, Lynn. And thank you so much for inviting me to give this talk. Let's see if I can share my screen. Does that work?
Looks great.
Okay, good. Thank you very much. So yeah, I'm going to talk about Venus and sort of discuss what we know about Venus' capabilities in defying the solar wind without what we like to call a magnetic shield. And Venus, of course, is this very interesting planet, and this sort of Earth-sized planet that is a little bit closer to the sun than Earth, but has this surprisingly thick, really hot and very dry atmosphere, barely containing any water, but it has this CO2-dominated atmosphere with 92 bars at the surface and 460 degrees Celsius, which is quite an extreme environment. And Venus is considered to most likely have started similarly to Earth. Potentially, it was this sort of water-rich planet with a global ocean of hundreds of meters, sort of this Earth-like state. We don't fully know exactly how it looked like, but there are indications that Venus might have started off similarly to Earth. However, today it's this dry, hot, hostile, sort of more hell-like state, if you will. And the billion-dollar question is, of course, how did Venus' atmosphere evolve from this sort of nice Earth-like place to this really hostile, hell-like place? And that also takes us, of course, to this question of how does an atmosphere really lose or transform an atmosphere? I really like this figure from one of the review papers, and many review papers on this very interesting topic, where they sort of try to summarize all of the different mechanisms that can affect this atmospheric evolution. But I would like to make it a bit more simpler, and I would consider that there are mainly two groups of pathways that can affect this atmosphere. The first one being sort of the solid planet atmosphere, surface atmosphere exchanges, chemistry, volcanism, etc. And the second group, I would like to call this atmosphere-space environment interaction, where you have these effects from solar radiation, the solar wind interaction, and the escape of particles from the atmosphere into space. And to me, of course, both are equally important to understand for the atmospheric evolution, because both of them probably contributed significantly. But in this talk, we will really focus on the second group, which is the atmosphere-space interface, and what do we know about this and how it could have affected the atmospheric evolution of Venus. So I said defying the solar wind without a magnetic shield. And when we talk about a magnetic shield, we usually talk about an intrinsic magnetic field such as that of Earth. This is a really simplified, maybe not perfectly ideal picture of how it could look like, but a planet that has an intrinsic magnetic field like Earth or Mercury or Jupiter can really try to withstand the solar wind pressure, the solar wind being this stream of charged particles coming from the solar wind, from the sun, sorry. Venus, on the other hand, does not have an intrinsic magnetic field. So instead, it has to rely on other mechanisms in order to sort of push away the solar wind. For Venus, which has a really thick atmosphere, this upper layer of the atmosphere is ionized by the solar UV radiation. And this creates this really conductive upper layer of ions and electrons, which is called the ionosphere. This conductive ionosphere then interacts with the solar wind and the interplanetary magnetic field, both originating from the sun, and creates what we would like to call an induced magnetosphere. An induced magnetosphere is very small and really adaptive to what happens in the upstream solar wind. And compared to the size of an intrinsic magnetosphere, such as that of Earth, which you can see here, Earth is about the same size as Venus, but this one is much, much bigger than that of an induced magnetosphere, such as that of Venus. An important thing about Venus is that this is really the only planet in our solar system that has this sort of purely induced magnetosphere. It's the only planet that does not have any sort of crustal or internal magnetic fields and has an atmosphere. You can compare, for example, with Mars, which is usually considered to be similar to Venus. But Mars has these crustal magnetic fields, which are quite strong for the size of the planet. And even though it has this induced magnetosphere as well, these crustal fields make it so that we usually talk about hybrid magnetosphere when we talk about Mars, which then means that Venus is really this good example of what the planet looks like if it doesn't have any magnetic fields. This is sort of a structure of how this sort of induced magnetosphere can look like, especially in terms of the magnetic field lines. So, as I said, the solar wind also carries with it this interplanetary magnetic field, and this sort of drapes around the planet, creating this somewhat simple but still complicated structure of like a long magnetotail behind the planet. In this figure, you have the sun to the left. Considering then that Venus does not have a magnetic field, but it has a really thick atmosphere, that puts bounds to what type of escape you can have from an Earth-sized planet, such as Venus. And here I gave some examples, and these are the ones that we usually talk about being the main ones from such a planet. Here I grouped them into the neutral escape and the ion escape. But you can also group them into different things like thermal and non-thermal escape. Thermal escape, usually we talk about Jeans escape or hydrodynamical escape. And simplified, it's basically that neutrals in the upper atmosphere have enough energy to overcome gravity and escape from the planet. Venus, being this CO2-dominated atmosphere, making it very hot in the surface, actually is opposite in the upper atmosphere. So the CO2 actually cools the upper atmospheric layer and makes it really, really cold. This means that the thermal escape for Venus is very, very low. It's very inefficient. And neutrals really don't escape that way. Neither lighter elements like hydrogen or heavier elements like oxygen. Another neutral escape that could be important is photochemical escape. This is basically a chemical reaction happening in the upper atmosphere where the end products sort of gain energy due to this chemical reaction, and that can lead them to overcome the escape, the gravity of the planet. For Venus, this is very small, especially for heavy things like oxygen. For hydrogen, it could be important, at least for some chemical reactions, but it's a bit underdeveloped still. For Mars, on the other hand, oxygen escapes quite significantly due to photochemical escape, so it's definitely different depending on the size of the planet. Another neutral escape that could be important for Venus is sputtering. Sputtering is when an energized particle sort of crashes into the upper atmosphere, and that sort of knocks out an additional number of neutral particles from the planet. And for Venus, it's really difficult to measure sputtering, and we don't really know exactly how much contributes to the total escape in terms of sputtering. There are modeling efforts that tells us that maybe it contributes with as much as 25% of the total escape, but it definitely doesn't seem to be the dominant escape mechanism. Instead, we have to talk about ion escape at Venus. Ions or charged particles are reacting to electromagnetic fields, which is basically what the solar wind and interplanetary magnetic field is inducing into this induced magnetosphere, and therefore they are more likely to escape from the planet. Here we can group it in many different ways. Here I talk about pickup ions, which is ions that get picked up by the solar wind convective electric field and carried away. As I said before, the induced magnetosphere is quite small compared to the planet, which means that part of the upper atmosphere, the exosphere, can extend far outside of the induced magnetosphere. And that means that if something is ionized in the solar wind, this sort of gets picked up by the solar wind and escapes. The other two groups, this tail outflow and cold ion outflow, is groups of where different electromagnetic fields inside of the induced magnetosphere and the magnetotail accelerates ions away from the planet with different types of mechanisms. And this is usually seen as the biggest escape, group of escape from the planet. I'm not going to go into detail exactly how these mechanisms work, just to leave you with that most of the escape for Venus is in the form of ion escape. And this means that it's very important for us to understand exactly how the solar wind interaction with the Venusian ionosphere really works and how this induced magnetosphere look like in order for us to interpret how the sort of Venus-space interface has affected the atmospheric evolution of Venus. We know this from measurements of the plasma environment at Venus, and there have been many missions, flybys, etc. But two of the main missions that were there is the Pioneer Venus Orbiter and the Venus Express mission. Pioneer Venus orbited Venus around the 80s, and it carried a quite extensive plasma suite, so it could measure these ions, electrons, and magnetic fields. And it sort of established this global picture of how an induced magnetosphere looked like and how much ions actually are escaping from the planet. They found a typical oxygen ion escape rate of around 10 to 25 oxygen ions per second, which is quite a lot, but not that much, actually. It's very similar to the current escape rates of oxygen from Earth. And then Venus Express arrived at Venus a few years later, so in around 2010s. It was also measuring, and this also carried some plasma instrumentation. In particular, it carried this Asper for ion and electron measurements, as well as magnetic fields. And the addition that this mission could add compared to Pioneer Venus was that we could look at the directions of these different ions, like how are they moving and in what directions and what is affecting these movements. And an interesting thing also about Venus Express is that they also measured the ion escape and found that they are about an order of magnitude lower than what was found by Pioneer Venus. And then when you see that, you start to think about why it could be this different. And one of the main reasons may be that the solar cycle was quite more extreme conditions during the Pioneer Venus orbiter compared to the Venus Express. Venus Express was there during a very quiet and sort of weak solar maximum compared to when Pioneer Venus orbiter was there. And the solar cycle affects things both like EUV radiation, but as well as the solar wind dynamic pressure and magnetic field strength. We can look at this in a bit more details. So here you have a figure where you have the escape rates, total escape rates from the planet on the y-axis. You have the energy of the escaping ions on the x-axis, and you have a bunch of different studies using many different techniques to calculate these escape rates. The range is around 10 to 24 to 10 to 25, 26, but you can see that they are grouped together into this Pioneer Venus measured this higher but lower energy ions, whereas Venus Express looked at higher energies and saw lower escape rates. And the main difference is that we can think about between these missions is, of course, that they were different missions. They have used different instruments, looked at different energy ranges and different time periods, such as the solar cycle. As well as that they use different assumptions and analysis tools to integrate the total escape rates. And so these results and this variation, this huge spread in results, I think both reflects measurement uncertainties as well as this intrinsic variability that we can see in the solar wind-Venus interaction, which we're going to dig a bit more into. One of the things that we can do is that we can look at the escape rate again on the y-axis versus how much energy is available in the solar wind at the time of the escaping ions. So basically, how much energy does the solar wind have that can potentially be transferred to the ionosphere and the ionospheric particles that can let them come above escape velocity and escape from the planet. What we can see here in this plot is that when we have more energy in the solar wind, the escape rates increase. This is sort of very nicely correlated to our thinking about energy-limited systems such as Venus. You can see that I also added the results from the Pioneer Venus mission here with an indication of approximately the average solar wind energy during the time of the Pioneer Venus measurements, and you can see that that partially explains the differences between the Venus Express and Pioneer Venus results. You can also see that the division here is between high EUV and low EUV cases. And for low EUV, you have this nice trend of increasing escape rates with the higher energy in the solar wind. But for the high EUV case, it looks like it's a bit lower, and it looks like maybe a V shape in the trend. So it's a bit more complicated relationship during the high EUV case, sort of corresponding to the solar maximum case. That again tells us that maybe the EUV and it means basically a higher ionization rate does not always mean that we have a higher escape rate, even though we create more ions that could potentially escape from the planet. One of the things that we found is that, and this is what Venus Express really could look at, because we can look at the directions everything is moving in. And one of the things that we found is that during solar maximum conditions, the ions doesn't seem to be sort of smoothly moving away from the planet. So if you look at this plot to the upper right, here is a flux map where the sun is to the right. You have the edge of Venus there in the right corner. And you have the edge of the induced magnetosphere with the dashed line. You have proton fluxes in the top row, oxygen ion fluxes in the bottom row, and you have the solar minimum to the left and the solar maximum to the right. The red fluxes here signifies ions that are moving away from the planet. This is the expectation. Anything that reaches above escape velocity is accelerated away from the planet. However, what we're seeing is a lot of blue boxes. Blue boxes or blue colors means ions that are moving back towards Venus again, just a direction sort of Venusward. And what you can see here is that at solar maximum, we have a lot of blue boxes quite far away from the planet. And this is a surprising thing. This significantly affects the total integrated escape rates from the magnetotail at Venus, and can partially explain why we have this complicated relationship at solar maximum. This is something that also this left plot shows you, where the red colored line here, again, we have escape rates on the y-axis, and here you have what EUV irradiance on the x-axis, and what you can see with the red line is how much is escaping sort of down tail, while the yellow one tells us how much is sort of moving back towards the planet, and you can see that they are sort of changing when you have an increase in the EUV. The physics of this is not fully understood, and this is one of the open questions for Venus. We think that this may involve magnetic reconnection, which is this magnetic fields sort of reconnecting with each other, releasing a lot of energy, and can make ions be accelerated back towards the planet. This is something that happens a lot at a magnetized planet, such as Earth or Mercury, but it's not really been thought to be active at magnetized planets, and it sort of complicates the picture of this really simple induced magnetosphere of Venus, and it's something that the measurements that we do have at Venus does not have enough sort of time spatial resolution in order for us to really fully characterize the physics of these returning flows. But there are indications that this probably is magnetic reconnection. So all of these results, it sort of tells us a story about an induced magnetosphere and the Venus ionosphere. And it sort of shows that the ionosphere is quite resilient under the changing solar wind. It sort of adapts and changes the entire environment when the solar wind itself changes. And so you can see different parts of the plasma environment adapting strongly to external conditions. For example, you can see that the ionospheric density is higher for solar maximum than solar minimum. This is highly connected to the ionization rates. Solar maximum usually means higher EUV fluxes, for example. We can see that the plasma flow patterns change quite significantly, like I showed you before. We can also see that the size of the induced magnetosphere, or even the entire plasma region, changes during the solar cycle. This is a very nice figure, I think. This is the bow shock, but it can sort of represent the interaction region. And what we show here is 3 different missions that show the size of this interaction region at Venus. So you have the Venera at 9 and 10 in green in the bottom left. You have the Pioneer Venus in blue, and you have the Venus Express in orange. And they all tell a very compelling story about the connection with the solar cycle from this gray line showing the monthly sunspot numbers. So the sunspot number doesn't tell us about the physics, but this nice correlation with the solar cycle shows us that Venus induced magnetosphere really adapts strongly to the changes in the solar wind. Another thing is the topology in the magnetic field draping. So I told you that the induced magnetosphere is basically composed of this interplanetary magnetic field draping around the planet and forming the long magnetotail. And these 2 figures, this to the right and also the one to the left, tells us that this sort of changes when the conditions upstream of Venus changes. So for example, in the upper left corner, you can see that the ionosphere, when it's quite strong, which happens usually when we have a high EUV or a solar maximum condition, or when we have a very low dynamic pressure that cannot really compress the ionosphere, we have this very resilient, very strong ionosphere, can push away everything that's coming towards the planet. However, when we have a low EUV or a solar minimum type condition, or when we have a very high dynamic pressure, everything gets really compressed and it almost collapses. So the interplanetary magnetic field can really penetrate into the upper layer of the atmosphere of Venus. And it completely changes how the induced magnetosphere actually looks like. And that is one of the things that really have these consequences for how the atmosphere, induced magnetosphere looks like for Venus. So it's quite cool, I think, how Venus is so sort of adapting all the time to how the the solar wind changes. One of the things that we can look more into is also the efficiency of the transfer of energy from the solar wind to the atmospheric ions. So we know that there's a correlation between the two, but how efficient really is this energy transfer? And in this study, we treated Venus sort of as a black box. We don't really care what happens in here. We care about what energy is available upstream. We care about what energy is sort of coming out from the planet in the form of escaping ions. And then we take a ratio between the two. We get the coupling coefficient, like how much in percentage, let's say, how much of the energy in the solar wind is actually being transformed to these ions that are escaping the planet. What we can see is that this is extremely low and very variable. There's no clear trends really of how this coupling looks like. More than maybe we can see that the coupling decreases slightly when we have more energy in the solar wind. So even though more energy is being sort of released from the planet when we have more energy in the solar wind, the sort of percentage of energy being transferred decreases. So Venus actually becomes better at protecting itself against the solar winds when the solar wind becomes stronger. And so there's not clear that a stronger forcing means a stronger atmospheric escape in that sense. Okay, so we looked at the average conditions. In the average conditions, you have a lot of time for Venus to adapt to what's happening and change its induced magnetosphere. But of course, an interesting thing is these extreme conditions, and this is something we usually talk a lot about. With extreme events, we usually talk about stuff like interplanetary coronal mass ejections or co-rotating interaction regions, or some kind of strong solar wind pressure enhancements, or we might even talk about solar flares or associated X-ray bursts, etc. All of these are very temporal things that can change things at Venus instantaneously. And that means that they are quite important because they can be short-lived, high energy input, but they can strongly sort of perturb the ionosphere and the induced magnetosphere for a short period of time. These extreme conditions were also probably more likely to happen earlier in the solar system. So we can study how they affect Venus today in order to understand how much they might have affected the planet earlier in the solar system's history. And this is a nice study where they looked at sort of a bunch of different events, such as these extreme events, especially ICMEs, and they compared that with when there are no extreme events there. So the average state before and during extreme events, and they saw that it only increased by maybe a factor of 2 the total escape rates during these extreme events. And so it doesn't really look like it's strongly affecting the induced magnetosphere and the atmospheric escape. However, there are a few studies that show, or at least discuss, the potential for these extreme events to enhance the escape rates by orders of magnitude. But we don't really have the temporal sort of resolution from an orbiting spacecraft to really understand such a short-lived event. If you have something that occurs for maybe just 24 hours, and the measurements you're using is an orbiter that has a 24-hour orbit, you don't really have so much data points to use to look at this and study it in detail. And so we need a lot more in order to understand fully how extreme events really affect Venus. But from the studies that we do have, we can see that they change a lot of things. They might change sort of the morphology or channels that the escape happens from. They may change which channel is the most strongest compared to the average state. And different events may change it differently. For example, an ICME is usually connected to a big rotation in this interplanetary magnetic field, which in itself then can cause this magnetic reconnection, etc., and really sort of bring away a lot of magnetic fields, and with it a lot of plasma from the planet. And so this is something that we are currently looking a lot into, but I think we don't fully understand it. So, okay, so we know a lot about the present day oxygen escape from Venus, and we can sort of think, okay, oxygen escaping from the planet, it can come from water. What does that really mean in terms of, the 4 billion years of the solar system? We can do this really, really simple exercise. We can start with the measured present day ion escape rates, such as the one here on the right, and we can assume that this interaction between Venus and the solar wind sort of scales in time. It was the same earlier, but maybe so we can assume that it was the same type of interaction. And then we can use the solar wind evolution, so how it changed in time. And we can combine the two and we can get sort of a total escape, like how many oxygen ions have escaped in the past 4 billion years, let's say. Using this, we can get some numbers. Okay, so we see that 10 to 16 kilograms of oxygen escaped from the planet. And that is equivalent to, if we assume all of that is water, we spread it over an entire globe of Venus, it would contribute to maybe a few decimeter, a half a meter of water, which is very, very small compared to the hundreds of meters of water that likely that is assumed to have existed on Venus earlier in its history. And so it sort of tells us that the present day ion escape cannot really explain the loss of Venus' entire water content. But the question is, these are big assumptions. Can we really make these sort of big assumptions in this simple exercise? And probably not, is the answer. But the question is if we can refine it, if we can make it better. We know that, for example, the atmosphere composition is quite important for how the upper atmosphere looked like. For example, I told you that Venus has a high CO2 content, the same as Mars. And this leads to a very efficient cooling of the upper atmosphere, which means that the upper atmosphere is quite compact and small and very cold. And here, for example, you have a figure, you have an altitude on the y-axis and you have the temperature on the x-axis. And you can see modern Venus and modern Mars temperature profiles in the atmosphere with altitude here down to the left. And you can see they are really cold and very sort of compact. They all end, these all lines end at the exobase, which is typically the upper limit of an atmosphere. If you look at modern Earth, you can see that it's quite much more extended and much, much hotter in the upper atmosphere. And this is because Earth has a different composition. We have a lot of nitrogen and oxygen instead of this very high CO2 content. And if you would place Earth or Mars at Venus today, they would be even more hot. And so it's quite interesting that Venus became this really cold, even though it's so close to the sun. But that also tells us that if the composition of the atmosphere changed with time for Venus, then obviously the entire premises of the assumptions would change. Maybe Venus would be much more extended in its atmosphere. As I told you before, the induced magnetosphere is quite small compared to the planet. So if the atmosphere, the neutral atmosphere itself would be bigger, extend further, it would extend further out from the induced magnetosphere, and that would probably change the entire interaction region. And how that would affect the escape rates backwards in time, that's quite tricky to extract. But how far back in time could we potentially go? That maybe tells us, maybe the EUV fluxes and the evolution of the EUV from the sun could tell us something about that. This shows you a curve of the sort of ratio between the current luminosity of the sun compared to how it changed in time. So we are today on the left side, and then we go backwards in time when we move to the right. And as you can see, the EUV flux increased in time. And the range, the orange arrows here show you the range of EUV fluxes that we see at Venus today due to, for example, the solar cycle. And with this, we can see that, okay, maybe at around 2.5, 3 billion years ago, This is the edge of where we would be able to sort of see the UV fluxes at Venus today and use that backwards in time. But of course, at that time, the UV fluxes also varied a lot in time. And so it's quite complicated. But maybe we can use the current assumptions back to maybe 2 billion, 3 billion years ago. But that probably changed also the escape efficiency. With all of that, it sort of leads us to this question of how energy really reaches the escaping ions and what mechanisms that we need in order to sort of transfer energy from the solar wind to the upper atmosphere of Venus and leave these ions to escape from the planet. And this is where we have a lot of open questions still. We have some measurements of this. We know that the plasma inside is sort of screened from direct solar wind pickup, but we know energy can reach the ions via different pathways like induced currents, Hall accelerations, wave particle interactions, such as the one, the graph to the left here shows you this sort of magnetic pumping by these magnetosonic waves, showing you that, okay, in the upper ionosphere, we might have some efficient wave pumping occurring. This is measurements from the Pioneer Venus orbiter. We also have some precipitating solar wind ions and ENAs, energetic neutral atoms. But many of these processes really require that we have a really high both time resolution, energy resolution, direction resolution, and that we have good sort of electromagnetic wave fields measurements. And this is something that was really lacking for the previous missions. Not because we didn't know that we might need that, but because when they were sort of going to Venus, we didn't know anything about Venus. We didn't even know how an induced magnetosphere looked like. And so they really showed us all of this information that we have. And now we can take that information and we can understand which type of instrumentation we would need to understand it more. And so I would say that we would need a new mission to Venus to really fully characterize how the escape or the interaction between the atmosphere and the solar wind really has affected the atmospheric evolution for Venus. And with that, I'd like to conclude this presentation. And I would say that Venus sort of is this really good planet that can provide a lot of lessons what happens or how a planet without a magnetic field or magnetic shield can work or produce its own sort of magnetic shield in a way. We know that escape to space matters for atmospheric evolution, but today's sort of oxygen loss is so small that it leaves us a lot of questions. Like, is this real or do we just not understand it fully? We know Venus-induced magnetosphere adapts quite efficiently to the solar wind. And these differences that we see between different missions may be because they actually were there at different time periods of Venus. But yeah, with that, we have a lot of open questions still about this energy transfer. How much does the extreme events really affect the planet? And how does the earlier solar system conditions in terms of both the sun itself, but also the atmospheric composition and structure of the atmosphere of Venus change? And so the final takeaway is that Venus really retains this really thick atmosphere, although not the water, even without a magnetic shield, which may be a lesson for other rocky planets or exoplanets. And with that, I would like to thank you for your attention. And if you have any questions, I'm open.
Thank you so much for this amazing presentation. I think a lot of people in the room agree with you that we should go back to Venus and that Venus is an interesting planet. Yeah, you're in good company here. If we have any questions, if anyone would like to raise their hand. I'm sure there's lots to talk about. I see, is it Rob? Is that you?
Yes, that's me.
Yes, please go ahead.
Hi, Mark. Thanks so much for amazing talk. So you actually kind of concluded with the thing that we should go back to Venus and take some more observations, like really characterize the atmosphere and what's escaping from it. But we do have a couple of upcoming missions towards Venus with like the whole decade of Venus going on. So are the current planned missions already equipped to give you these observations? And if not, what kind of instrument would they need?
So what I would like to say is that these missions are going to be amazing, of course, for understanding this question. But if I can go back to one of my first slides here. These missions that are going to Venus are gonna focus a lot on the first of these questions, sort of the solid planet atmosphere, which we still don't fully understand. Venus is very complicated, especially it's really difficult to reach the surface. So they are gonna characterize that part, which is important. But they will not really characterize anything in terms of the atmosphere space environment. Nothing above, say, 100 kilometers will realistically be observed with these missions. What instrumentation would they need? I have a lot of suggestions. I even have even sent a mission proposal to the ESA M8 selection, but it was not moved forward. But I think you would really need more detailed particle, like ion measurements, ionospheric, sort of neutral ion gas mass spectrometers. We need detailed electric field, magnetic field measurements. And I would also sort of encourage this coupling between the upper atmosphere, neutral atmosphere, and the ionosphere. There's a lot of complicated things happening there. We don't really understand how these ions reach above the escape velocity of Venus. This first few sort of energy that they need. So a lot. We need a lot.
That's quite a wish list.
Any other questions? I can also ask one if we wait for other people. I think a lot of people probably in the audience are like me, exoplanet people who sort of daydream about rocky exoplanet observations, which we obviously do not have. But I think the thing, my kind of, as an exoplanet person, my kind of takeaway from this is that, I mean, it sounds like it's really hard to understand the processes that are involved with atmospheric loss. Actually, you and I spoke about it recently, about a lot of exoplanet people talk about this cosmic shoreline where like exoplanets that are this close have an atmosphere, and if they're this close, they don't. And it's this kind of like two parameters. And I mean, just tell the people in the back, like, sounds like we should be careful about oversimplifying our escape models for exoplanets. Yeah, right? Can I get like your approve this message?
I mean, it's really difficult because we can, of course, go to the planets in our solar system, and we have these whatever 8 examples that we can.
It's hard enough to do that.
And we have the 3 ones that are like Earth-like, Venus, Earth, and Mars, and they are all so different, and they have so different compositions and interactions, and so I think just the distance from the sun is not really the full picture. But of course, if it's really close to the planet, like Mercury, then it's probably not going to have an atmosphere. So I can understand the simplification. Maybe with like an asterisk, you know.
What would, if we like extend the 2 parameters to like a 3D box kind of, like, what do you think is the next kind of most important parameter?
Right.
Sorry, that's a tricky question. I just accidentally made it up on the spot. I don't know.
No, I think it's a good question. So I guess the biggest thing when we talk about exoplanets is maybe the solar flux, like where is what's it called?
Cough, cough, TRAPPIST.
Yeah. But the next one would, I guess, be more the solar wind. It looks like if the solar wind is harsher, more extreme, then maybe it will be more difficult for a planet to retain the atmosphere. While if it's less extreme, maybe it's easier. For Venus, for example, this average state condition seems to be okay to withstand the solar wind from. So, and I think that's something when you change the star that it orbits around, it's going to change how the solar wind looks like, or stellar wind, I guess it's called.
Yeah.
So maybe that would be the next step to look at.
Interesting. Yeah, that's really interesting. Thank you so much.
Thank you.
Do we have any other questions in the audience?
I had a question. I wanted to follow up on
Sure.
that question about parameters.
Yeah.
I was really fascinated by your sort of notes and focus on the role of CO2 cooling, I think, if I got that right,
Yeah.
which is another factor that is, may be very different for different exoplanets or different, with different fractions of volatiles and other histories.
Right.
And so it seems like one of these, it'd be great to see someone, modelers and experimentalists, explore this in more detail. Is as the fraction of CO2 in the atmosphere increases, how does the resistance to loss change? Anyway, could you talk more about that? And again, from the exoplanet community. I'm very interested in how differences in CO2 fraction might result in different atmospheric lifetimes.
Yeah, it's a really interesting question and something that has been sort of started to be discussed a lot recently. So you might find studies from, for example, Michael Way, which I cite here. This is a review paper, but there are papers by Johnson and Helmut Lammer, for example, where they really discuss and show that it's not as simple as just sort of taking Earth and assuming things. Venus, the composition is important and the CO2 content is important. There seems to be this shift in when it cools enough and not at around, I don't remember exactly the numbers, I have to say, but maybe if you decrease it to like 70% instead of like, what is it now, 92%, 97%, this is where you have a huge shift in how the temperature and sort of the size of the atmosphere changes. But you have to look up the numbers in more detail. But this, I agree with you, is a really interesting question.
Thank you.
Thanks.
Then we have a hand up from Gwenelle. Sorry if I mispronounced your name.
Yeah, that's quite all right. Maybe to add to this topic, in Vienna, we have run such models where we compare both the chemical composition of an atmosphere and how this expands or contracts and keeps your atmosphere cool. Though this had a focus primarily on thermal losses and Jean's escape, so it's a bit different from what Noah presented, but it might be interesting. It was published in a paper last year in Astronomy and Astrophysics for those interested.
Really interesting, yes. And of course, that's an important point also, that this shift for modern Venus, the thermal escape is not really important, but if you change the composition, that will be a bigger portion. That's a really good point.
Yeah, could you add the link to that in the chat? Great, thanks.
Yeah, thanks. Do that.
Any other questions? Or comments? Nice comments. No, I think it's really, really awesome. I mean, I've been Team Venus for a long time. I think you can love all your children equally. I don't think you have to pick favorites, but Venus is the star of my solar system, I think.
Yeah. It's a star from Earth, I guess.
Yeah. But do you think, actually, I was thinking as well about the first question about, obviously there's 500 gazillion things. Oh, there's the link. Thank you so much. There's 500 gazillion things that you could measure. And I mean, best thing to do for Venus, I guess, go there, I don't know, build a base that can somehow withstand with robot stuff that can do all day, everyday geology. But I mean, do you think, would an orbiter kind of be enough if it's like, if we're looking at upper atmosphere, would you really need a lander for some of these questions? Or do you think the like surface atmosphere interactions are a bigger component than that? You know?
Right. So yeah, I think to address the questions that I am interested in, which is this interface between space and atmosphere.
Yeah.
an orbiter would be the best because you can then characterize. But then the orbiter would probably need to make these sort of deep dips into the atmosphere.
Right.
Because you have this sort of range, and this is true also for Earth. There is an altitude range where you cannot really fly with planes or balloons, and you cannot quite reach with spacecraft because the drag becomes too much.
Oh yeah, of course. Yeah, that's true.
So we call it the ionosphere because we don't really know that much about it. You can only use sort of remote sensing to look at it. And that region is really key, I think, for how this looks like. So we can try deep into that with an orbiter. A lander, definitely for the, the surface atmospheric conditions, we know maybe not enough. So I would love that, but that would probably die within 2 hours. So.
Soviet style, exactly. Maybe, okay, orbiter with a big bucket on a rope.
Exactly, yeah. Another idea is balloons. You can place balloons in different altitude ranges. And around the sort of the cloud layer, we can really place balloons and we can look into stuff. And then we can sort of look between the balloon and the orbit. So there are ideas, but of course, they all come with their respective challenges.
Of course, yeah.
If we can do like the Soviet and send everything, that would be amazing.
Exactly, just keep chucking them.
Yeah.
Such cool work, super interesting. Final call for questions. If you think of a question after this talk and you kick yourself for not remembering to ask it during that time, fear not, because you can, of course, also join us on our Discord channel where we can keep the conversation going if you have any other questions or comments that you think of. But aside from that, I just want to say a big thank you to Moa again for this awesome presentation, and thank you all for joining us here today. And I will also let you know that we have our next Rocky Worlds discussion will be, and I'm sorry because I think I'm mispronouncing this, but Miki Nakayama from the University of Rochester will be joining us for the next talk. So thank you all so much, and see you next month.
Thank you.